Let yourself sink deeper into comfort now. Feel the weight of your body pressing gently into the surface beneath you. With each breath, allow your muscles to soften, releasing any tension they've been holding throughout the day. Tonight, we're going to drift together through the cosmos, exploring the most peaceful and calming aspects of our universe. There's no need to focus too hard on any particular detail. Just let the words wash over you like gentle waves, carrying you toward rest. The universe is ancient, patient, and unhurried. It has been unfolding for nearly 14 billion years, and tonight, we have all the time we need to float through its most serene corners. Close your eyes if you haven't already, and imagine yourself suspended in the quiet vastness of space, weightless and free, surrounded by the soft glow of distant stars. Here, there are no deadlines, no obligations, only the eternal, peaceful rhythm of cosmic time. Let's begin our journey together. The infinite canvas, understanding the observable universe. When we look up at the night sky, we're witnessing something truly extraordinary. We're looking at light that has traveled for thousands, millions, sometimes billions of years just to reach our eyes. Every photon that enters our vision has been on a journey through the vast emptiness of space, carrying with it a story from somewhere far away and long ago. This is one of the most calming realizations we can have about the universe. That we are connected to everything we see, not through touch or sound, but through light itself, the universe's most patient messenger. The observable universe extends approximately 46.5 billion light-years in every direction from Earth. This distance is so immense that it challenges our capacity to comprehend it. A light-year, as you might know, is the distance light travels in 1 Earth year, moving at approximately 186,282 miles every single second. That means in just 1 year, light covers about 5.88 trillion miles. Now multiply that by 46.5 billion, and you begin to glimpse the scale of what we can observe. But here's where things become even more soothing. Despite this incomprehensible vastness, the observable universe has a certain elegant simplicity to it. When scientists measure the universe at the largest scales, they discover something remarkable. The universe appears relatively flat and uniform. Between scales of 30 to 200 megaparsecs, there seems to be no continued structure, a phenomenon astronomers have called the end of greatness. Beyond this scale, the universe doesn't present us with ever more complex patterns to decipher. Instead, it settles into a kind of cosmic evenness, a gentle uniformity that extends as far as we can see. Imagine floating in the center of an enormous sphere, 46.5 billion light-years in radius. In every direction you look, you see essentially the same thing. Galaxies, clusters of galaxies, vast filaments of matter, and enormous voids where almost nothing exists. This uniformity is deeply peaceful. It means that no matter where you are in the universe, your view would be statistically similar to ours. There is no edge, no center that matters more than any other point. The universe, in its grandest expression, treats all locations with democratic indifference. The observable universe contains approximately 2 trillion galaxies. Each of these galaxies holds between 100 million and 100 trillion stars. The numbers become so large that they lose meaning to our everyday experience, which is precisely what makes them so restful to contemplate. Our worries, our daily concerns, our anxieties about tomorrow, all of these shrink to insignificance when held against the backdrop of 2 trillion galaxies, each one a complete universe unto itself, filled with billions of suns that will never know we exist. Consider the gentle patience required for light to cross such distances. The most distant galaxy we've detected is classified as MOMZ14, existing at a time when the universe was still in its infancy. The light we see from this galaxy has been traveling for over 13 billion years. It left that galaxy when the universe was young, and it has been making its way through expanding space all this time, never stopping, never wavering, just steadily moving through the darkness at its constant speed. There's something profoundly calming about the constancy of the speed of light. In a universe where so much changes, where stars are born and die, where galaxies collide and merge, where even space itself is expanding, light moves at the same pace it always has. It doesn't hurry. It doesn't slow down. It simply continues, one photon at a time, crossing the vast gulfs between the stars. The expansion of the universe adds another layer of tranquility to our cosmic understanding. Space itself is growing, like the surface of a balloon being slowly inflated. This means that galaxies are moving away from each other, not because they're flying through space, but because the space between them is increasing. The farther apart 2 galaxies are, the faster the space between them expands. At a distance of about 13 billion light-years, galaxies appear to recede from us faster than the speed of light, not because they're actually moving through space at that speed, but because of how much space is being created between us and them. This expansion is gentle, patient, and inexorable. It has been happening for nearly 14 billion years, and it will likely continue for trillions of years into the future. There's no violence to it, no sudden changes. Just a steady, cosmic stretching that causes distant galaxies to slowly drift further and further away. Eventually, billions of years from now, galaxies beyond a certain distance will disappear from view entirely, not because they've ceased to exist, but because the space between us and them will be expanding so quickly that their light can never reach us. But this won't happen tomorrow or next year or even in the next billion years. The universe unfolds its changes on timescales so vast that from our human perspective, everything appears stable and unchanging. The constellations you see tonight are essentially the same ones your ancestors saw thousands of years ago. The stars will maintain their positions relative to each other for tens of thousands of years more. The universe is in no hurry. Even the concept of the observable universe is soothing in its implications. There's likely far more universe beyond what we can see. Some cosmologists estimate that the entire universe could be at least 250 times larger than the observable portion. Using sophisticated mathematical models, scientists suggest the whole universe might be at least 7 trillion light-years in diameter. But even if we could somehow see this far, we would still likely find the same kinds of galaxies, stars, and structures we observe in our cosmic neighborhood. The universe might even be infinite, extending forever in all directions with no boundary or edge. If that's true, then somewhere out there, incredibly far away, there might be other regions of space that look remarkably similar to our own, simply because with infinite space, every possible arrangement of matter must eventually repeat. It's a strange thought, but also an oddly comforting one. We are not alone in our uniqueness. We are part of an infinite expression of possibility. Every point in the universe has its own observable sphere, just like ours. If you could instantly transport yourself to a galaxy 45 billion light-years away, you would find yourself at the center of a new observable universe, one that overlaps partially with what we can see from Earth, but also extends in directions we cannot observe. The universe is full of these overlapping spheres of observation, each one offering a slightly different view of cosmic history, each one equally valid and equally centered. The mass of the observable universe is staggering yet precisely calculable. The ordinary matter we can detect, the atoms that make up stars, planets, and us, comprises about 4.8% of the total critical density. This works out to roughly 1.46 times 10 to the 53rd power kilograms. That's a number so large it requires 53 zeros after it. And yet, this is only the ordinary matter. Dark matter, which we cannot see but whose gravitational effects we can measure, makes up another 27% or so. Dark energy, the mysterious force driving the acceleration of cosmic expansion, accounts for roughly 68% of everything. These ratios are deeply satisfying in their consistency. Everywhere we look in the universe, we find the same proportions. This cosmic uniformity suggests that the universe operates according to simple, elegant principles that apply everywhere equally. There are no special rules for different regions of space, no cosmic favoritism. The laws of physics work the same way here as they do in galaxies billions of light-years distant. As we contemplate these vast scales, let yourself feel the perspective they provide. Any problem you're facing, any worry keeping you awake, exists in a context so small compared to the observable universe that it becomes almost invisible. This isn't to diminish the very real challenges we face in our daily lives, but rather to offer a wider frame of reference. The universe has been unfolding for 14 billion years. Stars have been born, lived their lives, and died countless times over. Galaxies have formed, merged, and scattered. And through it all, the universe has continued its patient, unhurried expansion, following the same physical laws, maintaining the same cosmic proportions, demonstrating a kind of eternal steadiness that we can draw comfort from. Tonight, as you drift towards sleep, you can know that you are part of this vast cosmic structure. Every atom in your body was forged in the heart of an ancient star, scattered into space, and eventually collected together to form you. You are literally made of stardust, and you exist within an observable universe that extends 46.5 billion light-years in every direction around you. You are simultaneously infinitesimally small and cosmically significant, a tiny part of an immense whole, connected to everything through the simple fact of existence. Let that vastness hold you. Let the scale of the universe be a soft blanket around your consciousness. There's no need to understand it all, no need to grasp every detail. Just rest in the knowledge that you are part of something far larger than yourself, something ancient and patient and unhurried. The universe will continue its slow, majestic unfolding whether we're awake or asleep, whether we're worried or at peace. It simply is, and that simple existence is enough. Stellar lullabies, the peaceful lives of stars. Stars are the universe's longest-burning candles, and their lives unfold with a patience that makes even geological time seem brief. When we look at the stars scattered across the night sky, we're seeing celestial objects that have been shining steadily for millions or billions of years, and many will continue to shine for billions more. There's something deeply soothing about this constancy, this reliable presence that has watched over Earth since long before the first living things emerged from the oceans. Let's begin with how stars are born, because even this process, while incredibly powerful, unfolds with a dreamlike slowness that invites calm contemplation. Stars form within vast clouds of gas and dust called nebulae. These clouds, composed primarily of hydrogen with a dash of helium and trace amounts of heavier elements, drift through space, cool and dark, spanning distances of hundreds of light years. They're patient places, these nebulae, where the densities are so low that a cubic centimeter might contain only 1,000 particles, far fewer than the vacuum we can create in laboratories on Earth, yet still thick by the standards of interstellar space. Within these clouds, some regions become slightly denser than their surroundings, perhaps because of the shock wave from a distant supernova, or simply through random fluctuations in the distribution of matter. Once a region becomes dense enough, gravity begins to take hold. The particles in this denser pocket begin to pull on each other, drawing more and more material inward. This process of gravitational collapse is slow and gentle at first. The cloud doesn't suddenly plummet inward. Instead, it gradually, over the course of hundreds of thousands or millions of years, begins to contract. As the cloud contracts, something wonderful happens. The center of the collapsing region becomes denser and hotter. The gravitational energy of the falling material converts into thermal energy, warming the core. The cloud also begins to spin faster as it contracts, following the principle of conservation of angular momentum. The same principle that causes a figure skater to spin faster when they pull their arms in. This rotation causes the collapsing cloud to flatten into a disk, with the densest, hottest material concentrated at the center. Eventually, after millions of years of patient contraction, the temperature and pressure at the core reach a critical threshold. The core becomes hot enough, around 15 million degrees Celsius, for hydrogen atoms to overcome their natural repulsion and fuse together, forming helium. This is nuclear fusion, the process that powers all stars, and when it begins, something extraordinary happens. The outward pressure from this fusion reaction balances perfectly with the inward pull of gravity. The star reaches a state of hydrostatic equilibrium, a perfect balance between forces, and it settles into what astronomers call the main sequence. This moment of balance is one of the most peaceful states in all of nature. A star on the main sequence is not struggling or straining. It's not working hard to maintain its existence. Instead, it has found a perfect equilibrium where every force is balanced by an opposing force. The immense pressure trying to crush the star inward is exactly matched by the pressure from fusion pushing outward. The star will remain in this balanced state for most of its life, shining steadily, neither growing nor shrinking significantly, just existing in perfect, calm equilibrium. Our Sun is currently in this stable main sequence phase, and it has been for about 4.6 billion years. It will remain in this phase for another 5 billion years or so before it begins to evolve. That's an extraordinarily long time, longer than life has existed on Earth, longer than Earth itself has existed. The Sun rises each morning not through any effort or struggle, but simply because it's following the natural physics of stellar equilibrium. It's not something the Sun chooses to do or has to work at. It's simply what happens when a star finds its balance. Different stars spend different amounts of time on the main sequence, depending on their mass. The relationship is counterintuitive at first. More massive stars burn through their fuel much faster than smaller stars. A star with 10 times the mass of our Sun might only spend 10 million years on the main sequence, burning bright and hot but brief. Meanwhile, a red dwarf star with only a tenth of the Sun's mass might remain on the main sequence for 1 trillion years, far longer than the current age of the universe. Think about that for a moment. The smallest, coolest stars that formed when the universe was young are still in their infancy. Not a single red dwarf that has ever formed has yet reached the end of its life. Every single one of these small stars is still slowly, patiently fusing hydrogen in its core, and will continue to do so for hundreds of billions or even trillions of years. They are the universe's most patient objects, burning so slowly and steadily that they will outlast nearly everything else. There's a profound peacefulness in contemplating stellar timescales. Even a relatively short-lived massive star shines for millions of years. A sun-like star shines for billions. The tiniest stars will shine for trillions. These timescales are so vast that they make even the longest human timescales, the rise and fall of civilizations, the geological transformation of continents, appear as brief flickers. Stars don't rush. They don't hurry. They simply shine steadily and patiently, converting mass into energy according to Einstein's famous equation, E=mc². The process of fusion itself is surprisingly peaceful when you understand what's happening. In the core of a star, hydrogen nuclei, protons, move at tremendous speeds because of the intense temperature. Occasionally, two protons collide with enough energy to overcome the electromagnetic force that tries to keep them apart. When they do, they can fuse together, forming a heavier nucleus and releasing a small amount of energy in the process. This energy release is what keeps the core hot enough for more fusion to occur. But here's the remarkable thing. Each individual fusion reaction releases only a tiny amount of energy. The reason stars shine so brightly is simply because there are so many fusion reactions happening, on the order of 10 to the 38th power reactions per second in the Sun's core. Each one adds just a tiny contribution, but together, they produce the steady, reliable outpouring of energy that we experience as sunlight. It's a perfect example of how small, consistent actions, repeated countless times, can create something magnificent and enduring. The energy produced in the core of a star doesn't immediately escape into space. Instead, it begins a long, slow journey outward through the star's interior. This journey can take thousands or even hundreds of thousands of years. Photons of light are constantly absorbed and re-emitted by the atoms in the star's interior, bouncing around in what physicists call a random walk. Each photon moves a tiny distance, gets absorbed, waits a moment, then gets re-emitted in a random direction. Slowly, through this random process, the energy works its way from the core toward the surface. By the time a photon finally reaches the star's surface and escapes into space, it has been transformed countless times. The high-energy gamma rays produced by fusion reactions in the core have been broken down into lower-energy visible light and infrared radiation. The photons that left the sun's core when human civilization was just beginning are only now emerging from the surface to begin their 8-minute journey to Earth. The light you see from the sun today carries energy that was produced deep in its core 100,000 years ago or more, during the Ice Age, when mammoths still walked the Earth. This slow progression of energy through a star contributes to its stability. Stars don't suddenly brighten or dim because they have these enormous reservoirs of energy stored in their interiors. Even if fusion in the core were to somehow stop suddenly, the star would continue to shine for thousands of years as it radiated away the energy already stored in its structure. Of course, fusion doesn't stop. It continues steadily, day after day, year after year, millennium after millennium, eon after eon. Different types of stars exist in our universe, each with its own gentle characteristics. The smallest stars, red dwarfs, are cool and dim, barely glowing with a deep orange or red light. They're so faint that we can't see any of them with the naked eye, even though they're by far the most common type of star in the galaxy. These patient little stars burn their fuel so slowly that they'll still be shining long after all the larger, brighter stars have exhausted their fuel and faded away. Yellow stars like our sun are middle-of-the-road stars. Not too big, not too small, not too hot, not too cool. They shine with a pleasant, steady yellow-white light, and they remain stable on the main sequence for billions of years. It's no coincidence that complex life has evolved on a planet orbiting such a star. The stability and longevity of yellow dwarf stars provides the reliable conditions necessary for evolution to unfold over billions of years. Larger stars, the orange and red giants, are stars that have moved beyond the main sequence. They've exhausted the hydrogen in their cores and have begun to fuse helium instead. This causes them to swell enormously, becoming hundreds or thousands of times larger than they were during their main sequence phase. These giant stars are paradoxically both powerful and delicate. They produce enormous amounts of energy, yet their outer layers are so tenuous, so spread out, that they're less dense than the best vacuum we can create on Earth. If you could somehow stand on a spacecraft inside a red giant's outer atmosphere, you might not even realize you were inside a star. Even the deaths of stars, while energetic, follow predictable, lawful patterns that unfold over long timescales. A star like our sun will eventually expand into a red giant, gently puffing off its outer layers to create a beautiful planetary nebula, a glowing shell of gas illuminated by the hot core of the dying star. This core will eventually cool and fade, becoming a white dwarf, an ember of the star that once was. This white dwarf will then slowly cool over trillions of years, eventually becoming a cold, dark remnant. But this fate lies billions of years in the future for our sun. For now, and for billions of years to come, it will continue to shine steadily, rising each morning, setting each evening, as reliable as anything can be in this universe. More massive stars end their lives in supernova explosions, the most energetic events in the universe short of the Big Bang itself. Even these violent events serve a cosmic purpose. They're the universe's way of enriching interstellar space with heavy elements. Every atom of carbon in your body, every atom of iron in your blood, was forged in the heart of an ancient star and scattered into space by a supernova explosion. We are quite literally made from the remnants of dead stars, connected to the cosmos in the most intimate possible way. But even supernovae, despite their violence, follow laws. They don't happen randomly or capriciously. They happen when a massive star reaches the end of its fuel supply, when the equilibrium that has sustained the star can no longer be maintained. The core collapses in a fraction of a second, rebounds, and sends a shockwave through the star that tears it apart. It's the inevitable end result of a massive star's life, as predictable and lawful as everything else in the universe. As you lie here tonight, photons of starlight that left their parent stars decades, centuries, or millennia ago are gently raining down on Earth, passing through your window, perhaps even through you. These photons have traveled unimaginable distances to be here, carrying energy that was generated in the core of a distant sun. Energy that has finally completed its journey to end here, now on this ordinary night. You are surrounded by starlight, bathed in the ancient glow of stars both near and impossibly far away. Let yourself feel the patience of the stars. They don't hurry through their life cycles. They don't rush their fusion reactions. They simply exist, balanced and stable, converting mass to energy at a measured pace, shining steadily through the darkness of space. They will continue to shine long after we've fallen asleep, long after we've woken, long after our brief human lives have passed into history. The stars are the universe's way of reminding us that some things are meant to endure, to persist, to shine steadily regardless of the passing of time. Rest in that patience. Let the steady burning of the stars be a lullaby that carries you towards sleep. Imagine yourself floating in space, surrounded by the gentle glow of a billion steady suns, each one a perfect balance of forces, each one patiently converting hydrogen to helium, each one adding its light to the cosmic tapestry. The stars ask nothing of you. They don't need your attention or your understanding. They simply shine, and in their shining, they offer us the most peaceful reminder that in a universe of constant change, some things remain beautifully, reliably constant. Cosmic wanderers, planets and their serene orbits. There's something deeply calming about the predictability of planetary motion. In a universe that can seem chaotic and random, the paths of planets around their stars follow mathematical patterns so precise that we can predict their positions thousands of years into the future or reconstruct where they were thousands of years in the past. This clockwork precision, this reliable celestial mechanics, has been a source of comfort and wonder for humans throughout history. When a planet orbits a star, it's not fighting against gravity or struggling to maintain its path. Instead, it's doing exactly what comes naturally given its velocity and the gravitational field it finds itself in. A planet in orbit is, in a sense, perpetually falling toward its star but moving sideways fast enough that it keeps missing. This creates the elliptical paths we call orbits, and once established, these orbits can remain stable for billions of years. Consider our own solar system, the 8 planets Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune have been following their respective orbits around the Sun for approximately 4.6 billion years. Day after day, year after year, millennium after millennium, they trace their paths through space with such consistency that we can set our clocks by them. Earth's orbit determines the length of our year. The Moon's orbit around Earth determines the length of our month. These cycles are so reliable that civilizations have based their calendars on them for thousands of years. The mathematics of orbital mechanics was worked out by Johannes Kepler in the early 1600s and later explained by Isaac Newton's law of universal gravitation. What Kepler discovered was that planets move faster when they're closer to the Sun and slower when they're farther away, following precise mathematical relationships. These laws of planetary motion aren't just descriptions of how planets happen to move. They're fundamental consequences of gravity and inertia working together. Any object orbiting any other object in space will follow these same laws, from satellites around Earth to planets around distant stars to stars orbiting the center of galaxies. There's a meditative quality to understanding orbital motion. Imagine Earth moving through space, following its elliptical path around the Sun. We're traveling at about 67,000 miles per hour in our orbit, yet we feel none of this motion. From our perspective on Earth's surface, it's the Sun that appears to move across our sky, rising in the east and setting in the west, returning to the same position after 24 hours. Meanwhile, Earth is also rotating on its axis once every 24 hours, a rotation that's been slowing down gradually over billions of years but remains remarkably steady. The Moon orbits Earth with the same kind of reliable patience. It takes about 27.3 days to complete one orbit, and during this time it rotates exactly once on its axis. This synchronous rotation, caused by tidal forces over millions of years, means the Moon always shows us the same face. There's a far side of the Moon that was completely unknown to humanity until spacecraft photographed it in the 1950s. The Moon's orbit is slowly increasing in distance from Earth, drifting away at about 1.5 inches per year as tidal forces gradually transfer angular momentum from Earth's rotation to the Moon's orbit. But this is such a slow process that it will be billions of years before the Moon drifts significantly farther away. Beyond our solar system, we've now discovered thousands of exoplanets, planets orbiting stars other than our Sun. As of late 2025, scientists have confirmed over 6,000 exoplanets, with thousands more candidates awaiting verification. These discoveries have revolutionized our understanding of planetary systems and revealed that planets are remarkably common in the universe. The first exoplanet orbiting a Sun-like star was discovered in 1995, a world called 51 Pegasi b. Before this discovery, many scientists thought planetary systems would all look relatively similar to our own solar system, with small rocky planets close to the star and large gas giants farther out. But 51 Pegasi b shattered this assumption. It was a planet as massive as Jupiter but orbiting its star in only 4 days, racing around at a distance where the star's heat would vaporize any known material. This was our first hot Jupiter, and it forced astronomers to completely rethink how planets form and migrate within their stellar systems. Since then, we've discovered an astonishing variety of planets. We've found super-Earths, planets larger than Earth but smaller than Neptune, which are apparently the most common type of planet in the galaxy, even though we don't have one in our solar system. We've found mini-Neptunes, ice giants, lava worlds where the surface is perpetually molten, planets that orbit two stars simultaneously like the fictional planet Tatooine from Star Wars, and planets that orbit pulsars, the collapsed cores of dead stars. One of the most fascinating discoveries is the TRAPPIST-1 system, located about 40 light-years from Earth. This system contains 7 Earth-sized planets orbiting a small, cool red dwarf star. 3 of these planets orbit within the star's habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. All 7 planets orbit closer to their star than Mercury orbits our Sun, but because their star is so much cooler than our Sun, some of them might have temperate climates. The entire system is so compact that if you stood on the surface of one of these planets, the other planets would appear larger in the sky than the Moon appears from Earth. You could watch neighboring planets pass across the face of the star, their round disks clearly visible to the naked eye. The orbits in the TRAPPIST-1 system demonstrate another beautiful feature of planetary systems: orbital resonance. Several of the planets are locked in orbital resonances with each other, meaning their orbital periods are related by simple ratios. For every 2 orbits one planet makes, another planet makes exactly 3 orbits. These resonances create a kind of gravitational harmony, with the planets' tugs on each other reinforcing rather than disrupting their orbits. The system is like a cosmic clock, with multiple gears turning at different but precisely related rates. Many exoplanets have been found orbiting within their stars' habitable zones, the region where conditions might be right for liquid water and potentially life. We don't yet know if any of these worlds actually harbor life, but the fact that such worlds exist in large numbers is itself a profound discovery. Current estimates suggest there may be billions of planets in our galaxy alone orbiting within their stars' habitable zones. We live in a universe that appears to be filled with worlds, many of them potentially Earth-like, many of them potentially capable of supporting life. The methods by which we detect these distant planets are themselves elegant and patient. The transit method involves watching a star and waiting for a planet to pass in front of it, causing a tiny, brief dimming of the star's light. This dimming might be only 1% or less, and it only happens during the brief time the planet crosses the star's disk as seen from Earth. Yet, by carefully monitoring thousands of stars for years, astronomers have found thousands of planets this way. The radial velocity method detects planets by measuring the tiny wobble they induce in their parent stars. As a planet orbits a star, the star also orbits their common center of mass, creating a subtle back-and-forth motion. This motion causes the star's light to be slightly Doppler shifted toward blue when the star is moving toward us, and toward red when it's moving away. These shifts are incredibly subtle, sometimes equivalent to measuring the speed of a person walking on the surface of a star hundreds of light years away. Yet modern instruments are sensitive enough to detect them. There's something profoundly peaceful about the idea that planets are simply following their natural orbits, neither gained nor lost but simply persisting in the paths that physics dictates. When you look up at Venus shining brilliantly in the evening or morning sky, you're seeing a planet that has been following its orbit for billions of years, that will continue to follow that orbit for billions more. Venus completes an orbit every 224.7 Earth days, and it's been doing so since long before Earth had continents, before it had oceans, before it had any life at all. Mars, glowing red in our night sky, takes 687 Earth days to complete its orbit. For thousands of years, humans watched Mars move against the background stars, sometimes moving forward, sometimes appearing to move backward in an optical illusion called retrograde motion. This behavior puzzled ancient astronomers, but we now understand it perfectly. When Earth, moving faster in its inner orbit, overtakes Mars, Mars appears to move backward against the distant stars, just as a slower car on a highway appears to move backward when you pass it. There's no mystery, no magic, just the simple geometry of orbital motion. Jupiter, the giant of our solar system, takes nearly 12 Earth years to complete one orbit. Saturn takes 29 years. These are stately, patient journeys around the Sun, and yet to the planets themselves, these orbits are simply the natural consequence of their positions and velocities. They're not traveling to a destination. They're simply moving, following the curved paths through space-time that gravity creates. Uranus and Neptune, the ice giants of the outer solar system, take 84 and 165 years, respectively, to orbit the Sun. Neptune has only completed one full orbit since its discovery in 1846. Think about that. We've barely watched this planet complete a single journey around the Sun, yet we can calculate its orbit with such precision that we know exactly where it will be 1,000 years from now. And it's not just the major planets that follow these reliable paths. Every asteroid, every comet, every piece of space debris follows its own orbit, determined by gravity and inertia. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, each on its own elliptical path. Most of these asteroids are in stable orbits that they've maintained for billions of years and will maintain for billions more. Some are in orbital resonances with Jupiter, their periods related to Jupiter's by simple fractions, just like the planets in the TRAPPIST-1 system. Comets follow highly elliptical orbits that bring them close to the Sun for brief periods before sending them back out to the cold outer reaches of the solar system. Halley's Comet returns every 76 years, regular as clockwork, and has been observed by humans for at least 2,000 years. Each return is predictable, calculable, expected. The comet isn't choosing to return. It's simply following the orbit that was set billions of years ago when it formed in the distant outskirts of the solar system. Even the smallest natural satellites, the moons of other planets, follow these same peaceful, predictable patterns. Jupiter has at least 79 known moons. Saturn has at least 82. Each one orbits according to the same laws that govern everything else. The large moons like Jupiter's Galilean satellites, Io, Europa, Ganymede, and Callisto, are in stable orbits that have existed for billions of years. Europa, covered in an ice shell with a liquid ocean beneath, completes an orbit around Jupiter every 3.5 days. It's been doing this since long before Earth formed. This predictability, this clockwork precision, is one of the universe's greatest gifts to us. It means that we live in a cosmos governed by laws, not by chaos or whim. It means that we can make predictions and plans, that we can understand and navigate this universe we find ourselves in. The planets don't need to remember their paths. They simply follow the geometry of space-time, the curvature created by mass and energy. As you drift towards sleep tonight, imagine the planets of our solar system all following their orbits. Mercury racing around the Sun every 88 days. Venus taking its time at 224 days. Earth, our home, completing its yearly journey. Mars at 687 days. And the giants beyond: Jupiter, Saturn, Uranus, Neptune, stately and patient in their distant orbits. All of them moving, all of them following their paths, all of them exactly where they should be, where physics says they must be. Extend that image outward. Imagine the thousands of known exoplanets, each in its own orbit around its own star. Imagine the billions or trillions more that must exist, waiting to be discovered. All of them following their orbits. All of them obeying the same simple laws of motion and gravitation. All of them patient, persistent, predictable. There's a profound peace in this image. The universe is not random. It's not arbitrary. It follows laws, beautiful mathematical laws that we've been able to discover and understand. And these laws work everywhere, from the smallest moon to the largest planet, from our solar system to systems hundreds or thousands of light years away. In this lawfulness, in this predictability, we can find rest. The planets will continue their orbits whether we're awake or asleep, whether we're worried or calm. They simply move, following their eternal paths through the darkness of space, reliable companions in the cosmic night. The silent symphony, light and electromagnetic waves. Light is perhaps the gentlest thing in the universe, yet it's also our primary connection to everything beyond our immediate reach. Every photon of light carries information about where it came from, what it passed through, how long it's been traveling. Light doesn't push or pull. It doesn't force its way through space. It simply moves steadily and patiently at its constant speed of 186,282 miles per second, covering the distance from the Moon to Earth in about 1.3 seconds, from the Sun to Earth in 8.3 minutes, from the nearest star system to Earth in 4.3 years. What we call light is actually just a small part of the electromagnetic spectrum, the narrow band of wavelengths that our eyes happen to be able to detect. This visible light ranges from violet, with wavelengths around 400 nanometers, to red, with wavelengths around 700 nanometers. A nanometer is 1/1,000,000th of a meter, incredibly tiny, yet light waves of different lengths in this narrow range create all the colors we can see. But the electromagnetic spectrum extends far beyond what our eyes can detect. At wavelengths shorter than violet, we have ultraviolet light, then X-rays, then gamma rays, increasingly energetic forms of electromagnetic radiation. At wavelengths longer than red, we have infrared radiation, then microwaves, then radio waves, stretching out to wavelengths measured in meters or even kilometers. All of these are fundamentally the same thing: oscillating electric and magnetic fields propagating through space, differing only in their wavelength and frequency. The universe produces electromagnetic radiation across this entire spectrum. Hot objects emit primarily in the infrared. Our own bodies glow in infrared light, radiating the heat we produce. If you had infrared vision, you could see people glowing against the cooler background, each person a source of gentle infrared light. The sun produces light across the entire spectrum, from radio waves to gamma rays, though it produces most of its energy in the visible and near-infrared ranges, conveniently right where our eyes are most sensitive. Hotter objects produce light shifted toward shorter wavelengths. A relatively cool red dwarf star produces mostly red and infrared light. Our sun, hotter than a red dwarf, produces white light, a mixture of all visible colors. Even hotter stars shine with a blue-white light. The very hottest stars and other extreme objects produce significant amounts of ultraviolet light, X-rays, and even gamma rays. One of the most peaceful electromagnetic phenomena in the universe is the cosmic microwave background radiation, often abbreviated as CMB. This is light that has been traveling through space for about 13.8 billion years, coming from a time when the universe was only about 380,000 years old. Before this time, the universe was too hot and dense for light to travel freely. It was a glowing plasma where photons were constantly being absorbed and re-emitted by charged particles. But as the universe expanded and cooled, it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. Suddenly, light could travel freely through space without being immediately absorbed. The light released at this moment has been traveling through the expanding universe ever since. As the universe has expanded, this light has been stretched to longer and longer wavelengths, cooling from the visible light it once was to microwaves today. The CMB has a temperature of about 2.7 Kelvin, just under 2.7 degrees above absolute zero. This makes it one of the coldest things in the universe, a gentle whisper from the early cosmos, uniformly bathing everything in space in its faint microwave glow. The CMB is remarkably uniform. No matter which direction we look, we measure essentially the same temperature to within about 1 part in 100,000. This extraordinary uniformity tells us that the early universe was remarkably smooth and homogeneous. The tiny variations that do exist in the CMB, slight differences in temperature of only a few millionths of a degree, represent the seeds of all future structure. Regions that were slightly denser than average would eventually collapse under their own gravity to form galaxies and galaxy clusters. The pattern of these tiny fluctuations in the CMB matches perfectly with the distribution of galaxies we see today, providing beautiful confirmation of our understanding of cosmic evolution. There's something deeply meditative about contemplating the CMB. It's everywhere all around us right now. It passes through you constantly, these ancient photons that have been traveling since the universe was young. You are, at this very moment, bathed in the afterglow of the Big Bang, in light that is older than any star, older than any galaxy, older than anything except the universe itself. This light has seen everything. The formation of the first stars, the assembly of the first galaxies, the long, slow evolution of cosmic structure. And it continues its journey, cooling and fading, but still present, still detectable, still carrying information about the universe's earliest moments. Another beautiful form of electromagnetic radiation is the gentle rain of starlight. At any given moment, photons from thousands of distant stars are reaching Earth's atmosphere, having traveled for years, decades, centuries, or millennia. Most of these photons pass harmlessly through the atmosphere and continue down to the ground, where they might strike a tree, a building, your skin. Each one represents a quantum of energy that left a star long ago and has finally completed its journey. When you look up at the stars on a clear night, your eyes are capturing photons that left those stars years or centuries ago. The photons entering your eyes at this moment began their journey before you were born, possibly before your parents or grandparents were born. Each photon traveled alone through the vast emptiness of space, never wavering from its path, never stopping, never accelerating or decelerating, just moving at light's constant speed until finally, after years of travel, it happened to enter your eye and be absorbed by a light-sensitive cell in your retina, triggering a signal to your brain, star. This is how we're connected to the cosmos, through light. We can't reach out and touch distant stars, but their light reaches us, carrying information about their temperature, their composition, their motion. By analyzing the spectrum of light from a star, spreading it out into a rainbow of colors, astronomers can determine what elements that star contains, how hot it is, how fast it's moving toward or away from us, whether it has planets, even whether those planets have atmospheres. One of the most beautiful manifestations of light's interaction with matter is the aurora, the northern and southern lights that dance in the skies near Earth's poles. These occur when energetic particles from the sun, traveling on the solar wind, interact with Earth's magnetic field and are channeled toward the poles. When these particles collide with atoms and molecules in the upper atmosphere, they transfer some of their energy, temporarily exciting electrons to higher energy states. When these electrons fall back to their normal states, they release the excess energy as light, green light from oxygen atoms about 100 to 200 kilometers up, red light from oxygen atoms higher up, blue and purple light from nitrogen molecules. The aurora is a perfect example of how gentle and beautiful electromagnetic phenomena can be. The same solar wind that creates the aurora also creates hazards for satellites and power grids during strong geomagnetic storms. But the visible aurora itself is pure beauty, curtains and waves of colored light dancing across the polar skies, constantly shifting and changing, never the same from one moment to the next. Indigenous peoples living in polar regions have watched the aurora for thousands of years, creating myths and legends to explain these mysterious lights. Now we understand the physics behind them, but this understanding doesn't diminish their beauty. If anything, knowing that we're watching the visible signature of solar particles colliding with atmospheric atoms makes the aurora even more wondrous. Light doesn't only come from astronomical sources. Bioluminescent organisms create their own light through chemical reactions. Fireflies flashing in summer nights, deep-sea fish luring prey with glowing appendages, certain fungi glowing softly in dark forests. Even this light is electromagnetic radiation, produced when electrons and molecules drop from excited states to lower energy states, releasing photons in the process. The mechanism is the same whether the light comes from a firefly or from a star billions of light years away. Radio waves, the longest wavelength form of electromagnetic radiation, play a special role in astronomy. Many astronomical objects that are invisible or faint in visible light shine brightly at radio wavelengths. The center of our galaxy, hidden from view by intervening dust clouds when we observe invisible light, can be studied in detail at radio wavelengths. Pulsars, rapidly rotating neutron stars, sweep beams of radio waves across space like cosmic lighthouses, some of them spinning hundreds of times per second and producing radio pulses with clockwork precision. Quasars, supermassive black holes actively feeding on matter in the centers of distant galaxies, can be enormously bright at radio wavelengths. Radio astronomy has revealed structures and phenomena invisible to optical telescopes. Enormous lobes of radio emission extending hundreds of thousands of light-years from galaxies. Detailed maps of the distribution of hydrogen gas throughout our galaxy. The cosmic microwave background itself was first detected as a faint radio hiss coming from all directions in space. Even though we can't see radio waves with our eyes, they're all around us. The faint radio emission from distant galaxies reaches Earth constantly. If we could see radio waves, the sky would be full of structure. Glowing clouds of gas, bright spots marking active galaxies, the uniform glow of the cosmic microwave background. It would be a completely different sky from what we see in visible light, yet it's the same universe, just revealed at different wavelengths. One particularly gentle form of electromagnetic radiation is the infrared glow of dust clouds in space. These clouds, too cold to emit visible light, glow softly in the infrared, radiating the heat they've absorbed from nearby stars or from starlight that has been absorbed and re-radiated. The famous pillars of creation in the Eagle Nebula, towering columns of gas and dust where new stars are forming, are visible in both visible and infrared light. In visible light, we see the dense columns silhouetted against the glowing nebula behind them. In infrared light, we can see through the dust and detect the newly forming stars hidden inside the pillars, glowing warmly in their dusty cocoons. The Spitzer Space Telescope, which operated from 2003 to 2020, was dedicated to infrared astronomy. It revealed a universe rich with structure invisible to optical telescopes. Dust lanes in galaxies, cool brown dwarf stars too dim to shine in visible light, the warm glow of exoplanets as they emit the heat they've absorbed from their stars. The James Webb Space Telescope, launched in 2021 and operational since 2022, observes primarily in the infrared and has revolutionized our view of the early universe, capturing images of galaxies so distant that their light has been traveling for over 13 billion years. All of this information reaches us as light, electromagnetic waves carrying energy and information across the vast distances of space. Light doesn't tire. It doesn't need to rest. It simply moves, photon after photon, wave after wave, carrying messages from distant corners of the universe to any receiver capable of detecting them. Whether it's visible light, infrared, radio waves, or any other form of electromagnetic radiation, it all moves at the same speed, all follows the same laws, all represents fundamentally the same phenomenon. Oscillating electric and magnetic fields rippling through space. As you rest here tonight, light from distant stars is reaching Earth, passing through the atmosphere, perhaps entering your room through a window. These photons have traveled for years or centuries to be here at this exact moment. They carry no message for you specifically, no meaning or purpose. They simply exist, moving as they must move, following the laws that govern electromagnetic radiation. And in their silent passage, they connect us to the universe in the most intimate way, through the universal language of light. Let that connection soothe you. Let the knowledge that you're surrounded by light from 1,000 different sources. Stars, galaxies, the cosmic microwave background, the sun's reflection from the moon, be a comfort. Light is gentle. It doesn't push or disturb, simply illuminates, warms, reveals, and it does so constantly, reliably, according to laws that have governed it since the beginning of time. Rest in that constancy. Let the gentle rain of photons be a lullaby, a reminder that the universe is full of beauty that reaches us across vast distances. Beauty that continues whether we're awake to observe it or fast asleep. Timeless travelers, comets, asteroids, and meteors. Among the most ancient objects in our solar system are the comets and asteroids, leftover building materials from the solar system's formation 4.6 billion years ago. These objects have been orbiting the sun, largely unchanged, for almost the entire history of the solar system. They're time capsules, preserving information about the conditions and materials present when the planets were forming. And they follow their orbits with the same patient inevitability as everything else in space. Asteroids are rocky or metallic bodies, most of them residing in the asteroid belt between Mars and Jupiter, though some have orbits that bring them closer to the Sun, occasionally even crossing Earth's orbit. The asteroid belt contains somewhere between 1 and 2 million asteroids larger than 1 kilometer in diameter, and millions more smaller ones. Despite this vast number, the asteroid belt is mostly empty space. If you could somehow stand on one asteroid, the next nearest asteroid would typically be too far away to see clearly with the naked eye. The asteroids formed from material in the early solar system that never accumulated into a planet, largely because of Jupiter's powerful gravitational influence. Jupiter's gravity stirred up the material in this region, causing objects to collide at speeds too high for them to stick together and grow into a planet. So instead of one rocky planet between Mars and Jupiter, we have millions of smaller bodies, each on its own independent orbit. Some asteroids are bare rock, their surfaces baked by the sun. Others contain significant amounts of metal, iron and nickel primarily, possibly fragments of the cores of larger bodies that were shattered by ancient collisions. Still others are primitive, relatively unchanged since the solar system's formation, containing organic compounds and water ice along with rocky material. These primitive asteroids are particularly interesting because they might preserve organic molecules from the early solar system, and some scientists think that impacts from such asteroids might have delivered organic material and water to the early Earth, possibly contributing to the emergence of life. The largest object in the asteroid belt is Ceres, big enough to be round and now classified as a dwarf planet. Ceres has a diameter of about 960 kilometers, and it contains about a third of all the mass in the asteroid belt. Despite being the largest asteroid, Ceres would look small compared to Earth's moon, which has a diameter of about 3,475 kilometers. Still, Ceres is large enough to have differentiated into layers, with a rocky core, an icy mantle, and a thin, dusty outer crust. Observations suggest it might even have a subsurface ocean of liquid water, maintained by heat from radioactive decay in its interior. Most asteroids, however, are much smaller than Ceres. Vesta, the second most massive object in the asteroid belt, has a diameter of about 525 kilometers. After that, asteroid sizes drop off sharply. The vast majority of asteroids are irregularly shaped chunks of rock, too small for their own gravity to have pulled them into spheres. They tumble through space, rotating slowly, following their orbits, largely unchanged for billions of years. There's something deeply peaceful about this stability. These asteroids have been following their orbits for longer than Earth has had continents, longer than Earth has had life, longer than Earth has had oceans. They were here when the solar system was young, and they'll still be here long after human civilization has become a distant memory. They simply persist, patient travelers following paths set billions of years ago. Comets are different from asteroids, though equally ancient. Comets are mixtures of ice, rock, and dust, sometimes called dirty snowballs. Though the reality is more complex, most comets originate in two distant reservoirs. The Kuiper Belt, a region beyond Neptune containing millions of icy bodies, and the Oort cloud, a vast spherical shell of cometary nuclei surrounding the entire solar system at distances up to 100,000 astronomical units or more. The Oort cloud is so distant that it's barely connected to the Sun gravitationally. Objects there take millions of years to complete a single orbit. Occasionally, the gravitational influence of a passing star or a close encounter with a large Kuiper Belt object will slightly alter the orbit of an Oort cloud comet, sending it falling toward the inner solar system. This journey takes thousands or millions of years. The comet slowly picks up speed as it falls sunward, accelerating as the sun's gravity pulls it inward. When a comet approaches the inner solar system and begins to warm up in the sun's heat, something beautiful happens. The ice in the comet begins to sublimate, transforming directly from solid to gas without passing through a liquid phase. This releases gas and dust that forms a glowing cloud around the comet's nucleus called a coma, and solar wind and radiation pressure push some of this material away from the sun, creating the comet's characteristic tails. Comets typically have two tails: a bluish ion tail made of charged particles being blown by the solar wind, and a white dust tail made of dust particles being pushed by solar radiation pressure. These tails always point away from the sun, regardless of which direction the comet is moving. The tails of comets can extend for millions of kilometers, yet they're extraordinarily tenuous. The density of material in a comet's tail is far lower than the best vacuum we can create on Earth. If you could somehow fly a spacecraft through a comet's tail, you might not even notice you were passing through anything. Yet from Earth, these tails can be spectacular, stretching across large portions of the sky when a bright comet passes close to the sun. Most comets that visit the inner solar system are on highly elliptical orbits that bring them close to the sun for brief periods before sending them back out to the cold outer solar system or beyond. Some, like Halley's Comet, return relatively frequently. Halley's Comet has an orbital period of about 76 years and has been observed by humans for at least 2,000 years. Others are on orbits so elongated that they won't return for tens of thousands of years, or they're on hyperbolic trajectories that will carry them out of the solar system entirely, never to return. Each time a comet passes close to the sun, it loses some of its ice and dust to sublimation. Eventually, after many passages, a comet will lose most of its volatile material and become inert, indistinguishable from an asteroid. Some of the asteroids we observe today might be extinct comets that have exhausted their ice. The solar system is full of these objects in various stages of their life cycles, each one a fossil from the early solar system, each one carrying information about conditions 4.6 billion years ago. When tiny pieces of debris from comets or asteroids enter Earth's atmosphere at high speed, they create meteors, the streaks of light we commonly call shooting stars or falling stars. These events are completely harmless and actually quite beautiful. A typical meteor is caused by a particle no larger than a grain of sand entering the atmosphere at speeds of 20 to 70 kilometers per second. The friction with air molecules causes both the particle and the air around it to heat up and glow, creating the brief streak of light we see from the ground. Most meteors burn up completely in the atmosphere at altitudes of about 80 to 100 kilometers, never reaching the ground. The particles that create them are vaporized, their atoms becoming part of Earth's upper atmosphere. If you watch the night sky patiently for an hour, you'll typically see several meteors even on an ordinary night. These are called sporadic meteors, caused by random particles of dust scattered throughout the inner solar system. Several times a year, Earth passes through the dusty trail left behind by a comet, and we experience a meteor shower. During a meteor shower, you might see dozens or even hundreds of meteors per hour, all appearing to radiate from a particular point in the sky called the radiant. Meteor showers are named for the constellation where their radiant is located. The Perseid meteor shower in August has its radiant in the constellation Perseus. The Leonid meteor shower in November has its radiant in Leo. The Geminid meteor shower in December has its radiant in Gemini. These meteor showers are remarkably predictable. We know exactly when Earth will pass through each cometary debris stream because we know Earth's orbit precisely and we've mapped out where the debris streams are located. The Perseids peak around August 12th every year, created by debris from Comet Swift-Tuttle, which orbits the Sun once every 133 years. Even though the comet itself last passed through the inner solar system in 1992 and won't return until 2026, its debris trail remains in space, and Earth passes through it annually. There's something wonderfully reliable about this. Every August, the Perseid meteors return. Every November, the Leonids return. Every December, the Geminids return. The universe provides these annual displays with perfect consistency, asking nothing of us in return, simply offering up these brief moments of beauty to anyone patient enough to watch. Very rarely, a larger object, a small asteroid or a large meteoroid, enters Earth's atmosphere and survives the passage to reach the ground. When this happens, the object is called a meteorite. Most meteorites are pieces of asteroids, broken off in ancient collisions in the asteroid belt. Some are pieces of the Moon or Mars, blasted off those bodies by asteroid impacts and eventually falling to Earth. A few come from comets, though cometary meteorites are rare because cometary material is more fragile and less likely to survive atmospheric entry. Scientists prize meteorites because they're samples of extraterrestrial material that we can study in laboratories without having to launch expensive missions to collect them. Meteorites have taught us enormous amounts about the composition of asteroids, the age of the solar system, and the processes that occurred as the planets were forming. The oldest meteorites, primitive chondrites containing small round inclusions called chondrules, are among the oldest solid objects in the solar system, preserving materials from the solar nebula itself. Everything in this story, the asteroids, the comets, the meteors, the meteorites, speaks to the ancient history of our solar system and to the patient, predictable nature of celestial mechanics. These objects have been following their orbits for billions of years. They don't question their paths or struggle against them. They simply exist, moving as they must move, obeying gravity and inertia, occasionally providing us with spectacular shows when they catch sunlight at just the right angle, or when their debris burns up in Earth's atmosphere. As you rest tonight, know that right now, countless asteroids are following their orbits in the asteroid belt. Countless comets are slowly circling the sun in the distant Oort cloud. Somewhere, a meteor is blazing through Earth's atmosphere, briefly brilliant, then gone. These phenomena continue without pause, without rest, simply because that's what the universe does. It moves, it orbits, it shines, it follows its laws. And in this ceaseless but predictable motion, there's a deep peace to be found. The peace of knowing that the universe operates according to principles we can understand, that it will continue to do so long after we're gone, that we're part of something far larger and far older than ourselves. Galactic gardens, nebulae and star nurseries. Nebulae are among the most beautiful objects in the universe. Vast clouds of gas and dust where new stars are born, or the gentle remnants of stars that have died. They come in many varieties, each one spectacular in its own way, each one following the quiet, patient laws that govern how matter behaves in space. Looking at images of nebulae, you see intricate structures, glowing clouds, dark silhouettes, and swirling patterns, all created by natural processes playing out over thousands or millions of years. The word nebula comes from the Latin word for cloud, and it's an apt description. Nebulae are indeed clouds, enormous accumulations of gas and dust floating in interstellar space. But calling them clouds hardly captures their scale. Some nebulae are dozens or hundreds of light years across. If you could somehow stand at one edge of a large nebula, the opposite edge would be so far away that light would take decades or centuries to cross from one side to the other. There are several different types of nebulae, each with its own character and origin story. Emission nebulae are perhaps the most colorful. These are clouds of gas that glow because of energy they receive from nearby hot stars. The most famous emission nebula is probably the Orion Nebula, visible to the naked eye as the middle star in Orion's sword. The Orion Nebula is a stellar nursery, a region about 24 light-years across where new stars are actively forming. At its center are several very hot, very young stars that pump out intense ultraviolet radiation. This radiation ionizes the surrounding hydrogen gas, stripping electrons away from hydrogen atoms. When these electrons eventually recombine with the hydrogen nuclei, they emit light, primarily at a characteristic red wavelength called hydrogen alpha. This gives emission nebulae their characteristic reddish color in photographs, though long exposure images also reveal blues and greens from ionized oxygen and other elements. The Orion Nebula is relatively close to us, only about 1,350 light-years away, making it one of the most studied star-forming regions in the sky. Observations of the Orion Nebula have revealed hundreds of young stars in various stages of formation, many of them surrounded by protoplanetary disks, flattened clouds of gas and dust that will eventually condense into planetary systems. We're watching planetary systems being born, seeing the same processes that created our solar system playing out in real time, albeit on timescales of thousands or millions of years. The beauty of emission nebulae isn't just visual. There's a profound elegance to the physics involved. Hot stars produce ultraviolet photons. These photons travel through space until they encounter a hydrogen atom. the photon gets absorbed, kicking the hydrogen's electron into a higher energy state. Eventually, the electron falls back to a lower energy state, emitting a new photon in the process. This new photon might be absorbed and re-emitted by another atom, or it might escape the nebula entirely and travel through space, perhaps eventually entering a telescope on Earth where it's captured, recorded, and turned into part of the beautiful images we see. Each individual interaction, each absorption and re-emission of a photon is a simple quantum mechanical event. But billions upon billions of these events occurring throughout the vast volume of a nebula create the glowing clouds we observe. It's emergence in action. Simple rules, repeated countless times, creating complex beauty. Reflection nebulae work differently. Instead of emitting their own light, they reflect light from nearby stars. The dust particles in these nebulae scatter starlight, much like how Earth's atmosphere scatters sunlight to create our blue sky. Blue light scatters more efficiently than red light, so reflection nebulae typically appear blue in color photographs. A classic example is the nebulosity around the Pleiades star cluster. When you photograph the Pleiades with a long exposure, you see that the bright blue stars are surrounded by blue nebulosity, wisps and clouds of dust reflecting the star's light. There's something gentle about reflection nebulae. They're not producing their own light through violent processes or intense radiation. They're simply reflecting what's already there, like a mirror or a cloud lit by moonlight. They're part of the interstellar medium, the thin gas and dust that fills the space between stars, made visible by their proximity to bright stars. Dark nebulae are regions where dense clouds of dust block the light from stars or glowing gas behind them. They appear as dark patches or silhouettes against brighter backgrounds. The most famous dark nebula is probably the Horsehead Nebula in Orion, which appears as a horse's head silhouetted against the red glow of the emission nebula behind it. Dark nebulae aren't actually darker than their surroundings in any absolute sense. They simply contain enough dust to block visible light from passing through them. If you could observe them in infrared light, you'd often see stars forming inside these dark clouds, glowing warmly in their dusty cocoons. The Horsehead Nebula itself is a small portion of a much larger complex of gas and dust in the Orion constellation. The horse's head shape is created by a dense cloud of dust that happens to have a distinctive outline when viewed from our particular vantage point. From a different direction in the galaxy, it wouldn't look like a horse's head at all. It's simply a denser knot within a larger cloud, made famous by our particular perspective and by the bright nebulosity behind it that provides contrast. Dark nebulae remind us that much of the universe is invisible to our eyes. Between the stars, space is not completely empty. There's gas, primarily hydrogen, with a density of about 1 atom per cubic centimeter in typical interstellar space. There's dust, tiny solid particles, typically smaller than the wavelength of light, composed of carbon, silicates, and other materials. This dust is produced in the outer atmospheres of old red giant stars and is scattered into space when those stars shed their outer layers. Over time, this dust becomes part of the interstellar medium, blocking and scattering light, absorbing radiation and re-emitting it at longer wavelengths. Planetary nebulae are another type entirely, despite their misleading name. They have nothing to do with planets. They were named by early observers who thought they looked like the pale disks of planets in telescopes. Planetary nebulae are actually the outer layers of dying stars, gently puffed off into space when a star like our Sun reaches the end of its life. When a star like the Sun exhausts the hydrogen in its core, it begins to evolve off the main sequence. It expands into a red giant, its outer layers swelling outward to enormous size. Eventually, the star's core becomes hot enough to fuse helium into carbon and oxygen. But stars in this mass range can't generate enough temperature and pressure to fuse carbon and oxygen into heavier elements. Once the helium is exhausted, the core contracts and heats up, but fusion stops. Meanwhile, the outer layers of the star, weakly bound to the core, are gently expelled into space through stellar winds and pulsations. This expelled material forms a planetary nebula, a glowing shell of gas expanding outward from the dying star. The hot core of the star, now exposed, produces intense ultraviolet radiation that ionizes the expelled gas, causing it to glow. The result is one of the most beautiful phenomena in astronomy. A perfect or near-perfect ring or shell of glowing gas, expanding outward at about 20 to 30 kilometers per second, illuminated from within by the dying star at its center. The Ring Nebula in the constellation Lyra is perhaps the most famous planetary nebula. It appears as a nearly perfect ring of glowing gas, about 1 light-year in diameter, expanding outward from its central star. The colors and long exposure images are exquisite. Reds from hydrogen, greens and blues from oxygen, subtle variations created by the different densities and temperatures throughout the nebula. The central star, now a white dwarf, the exposed core of the original star, shines with a blue-white light, intensely hot but quite small, about the size of Earth but with the mass of our Sun. Planetary nebulae are transient on cosmic timescales. They last for only about 10,000 to 20,000 years before they expand and fade, their gas dispersing into the interstellar medium to eventually become part of new generations of stars. But during their brief existence, they're among the most beautiful objects in the sky, and they serve a crucial role in the cosmic cycle. The gas they return to space is enriched with heavy elements created during the star's lifetime. Carbon, nitrogen, oxygen, and other elements forged in the star's interior are scattered into space, where they'll eventually be incorporated into new stars, new planets, perhaps new living things. We are made partly from material ejected by stars in planetary nebulae billions of years ago. Another beautiful class of nebulae are supernova remnants. These are the expanding shells of gas created when massive stars explode as supernovae. Unlike the gentle puffing off of outer layers that creates planetary nebulae, supernova remnants are created by catastrophic explosions that tear stars apart in seconds. The shock waves from these explosions slam into the surrounding interstellar medium at thousands of kilometers per second, heating the gas to millions of degrees and creating expanding shells of glowing material. The Crab Nebula in the constellation Taurus is perhaps the most famous supernova remnant. It's the expanding debris from a supernova that was observed by Chinese astronomers in the year 1054. For several weeks, the supernova was bright enough to be visible during the day. Nearly 1,000 years later, we can still see the expanding remnant of this explosion. The nebula is about 11 light-years across and still expanding at about 1,500 kilometers per second. At its center is a pulsar, a rapidly rotating neutron star that's the collapsed core of the star that exploded. This pulsar rotates 30 times per second, sweeping beams of radiation across space like a cosmic lighthouse. Supernova remnants are beautiful invisible light, but they're even more spectacular at other wavelengths. In X-ray images, supernova remnants glow with the energy of gas heated to tens of millions of degrees. In radio images, we see the magnetic fields and relativistic particles created in the explosion. Each wavelength reveals different aspects of these complex structures, each one showing us physics at work in the aftermath of stellar death. The pillars of creation in the Eagle Nebula might be the most iconic image of star formation ever captured. Photographed by the Hubble Space Telescope in 1995 and again in higher resolution in 2014, the image shows towering columns of gas and dust, several light-years tall, silhouetted against the brighter nebula behind them. These pillars are star-forming regions. The dense gas and dust in the pillars is slowly collapsing under its own gravity, fragmenting into clumps that will eventually form new stars. At the tips and along the edges of the pillars, you can see small knots of denser material called evaporating gaseous globules or EGGs. These are regions where stars are actively forming, cocooned in their own small clouds of gas and dust. The hot young stars nearby are gradually eroding the pillars with their intense radiation, causing the gas to evaporate, hence the name. Eventually, the pillars will be destroyed by this radiation, but new stars will have formed in the meantime, continuing the cycle of stellar birth and death that has been ongoing in the galaxy for billions of years. In infrared images of the pillars of creation, captured by the James Webb Space Telescope, we can see through the dust to observe the young stars inside the pillars more clearly. The infrared light reveals a rich population of stars at various stages of formation, some still deeply embedded in their dusty cocoons, others beginning to emerge. It's a glimpse into stellar nurseries, a view of the birth process of stars. There's something deeply peaceful about observing these star-forming regions. The processes are energetic, gas is being heated, compressed, ionized, but they unfold over such long timescales that from our perspective, they appear frozen in time. The pillars of creation looked essentially the same 100 years ago as they do today. They'll look essentially the same 100 years from now. The changes occur too slowly for human lifetimes to perceive them directly. We see only a single frame in a movie that's been playing for millions of years and will continue for millions more. Nebulae come in all shapes and sizes. Some, like the Great Orion Nebula, are bright and obvious even in small telescopes. Others are faint and diffuse, requiring long photographic exposures to reveal. Some have distinctive shapes, the horse head, the eagle, the cat's eye, that make them easily recognizable. Others are irregular clouds without clear structure. But all of them are windows into the processes that govern the universe. How matter behaves in space, how stars form and die, how material cycles from stars to interstellar space and back again. When you look at images of nebulae, you're seeing these processes in action. You're seeing gravity slowly pulling gas together, eventually creating enough density for stars to form. You're seeing radiation from hot stars ionizing surrounding gas, causing it to glow. You're seeing the final gasps of dying stars as they return their enriched material to space. You're seeing the aftermath of supernovae, the violent deaths of massive stars. Each nebula tells a story, And each story is part of the larger narrative of how the universe operates, how matter transforms, how energy flows from place to place. As you drift towards sleep tonight, imagine yourself floating through a nebula. Around you, clouds of glowing gas stretch in all directions, illuminated by hot young stars. The colors are vivid, reds, blues, greens, created by different elements emitting light at their characteristic wavelengths. The density is so low that you wouldn't feel anything, yet you're surrounded by enough material to make thousands of stars. Time moves slowly here. Stars are forming, but it takes millions of years. The gas clouds shift and change shape, but so slowly that they appear static from any human perspective. There's no sound here. Sound requires air to travel through, and even a dense nebula is far more tenuous than Earth's atmosphere. There's only silence and light and the slow, patient process of creation as gravity does its work. Stars are being born around you, inside the densest knots of gas. They're small now, glowing dimly with the heat of gravitational contraction. But give them another few 100,000 years and they'll begin fusion, becoming proper stars, adding their light to the nebula's glow. This is the universe at work. This is how stars are made, how planetary systems form, how life eventually becomes possible. It all starts here, in these clouds with nothing but hydrogen, helium, a little dust, and gravity. From these simple ingredients, everything else follows. Stars, planets, atmospheres, oceans, life, consciousness, the ability to look back at the nebulae and understand them. We are products of stellar nurseries, born from processed stellar material, our very existence dependent on the slow, patient cycles of cosmic creation and destruction. Rest in that knowledge. Let the beauty of nebulae be a gentle reminder that the universe is constantly creating, constantly cycling material, constantly giving birth to new stars and planets. The processes are slow but inexorable, following physical laws that have been constant since the beginning of time. There's a profound peace in this constancy, this reliability, this patient unfolding of natural processes. The universe knows what it's doing, even if it's not conscious, even if there's no plan or purpose. Simply follows its laws and beauty emerges. Gravitational grace, black holes and space-time. Black holes might seem like frightening objects, but when you understand them properly, they're actually some of the most elegant and peaceful objects in the universe. They're regions where gravity has become so strong that not even light can escape. Yet they don't rage or hunger or actively pull things in. They simply sit in space, warping it around themselves according to Einstein's equations, patiently waiting for anything that happens to pass close enough to fall in. Let's start with the basics. A black hole forms when a massive amount of matter is compressed into an extraordinarily small volume. The most common way this happens is when a massive star, at least 8 to 10 times the mass of our Sun, reaches the end of its life and explodes as a supernova. During this explosion, the star's core collapses. If the core is massive enough, it collapses all the way down past the neutron star stage into a black hole. All of the core's mass gets compressed into a region of space with zero volume, a mathematical point called a singularity, where the density becomes infinite and the laws of physics as we currently understand them break down. Surrounding the singularity is the event horizon, often thought of as the surface of a black hole, though it's not a physical surface you could touch. The event horizon is the boundary at which the escape velocity equals the speed of light. Inside the event horizon, nothing can escape. Not matter, not light, not information. Once something crosses the event horizon, it's lost to the outside universe forever, from our perspective at least. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole with 10 times the Sun's mass, the radius would be about 30 kilometers. Here's what's peaceful about this. From outside the event horizon, a black hole behaves just like any other massive object. If you were orbiting a black hole at a safe distance, it would be no different from orbiting a star of the same mass. The gravity follows the same inverse square law. If our Sun were suddenly replaced by a black hole of equal mass, Earth's orbit wouldn't change at all. We'd continue orbiting at the same distance with the same period, just as we do now. We'd lose the Sun's light and warmth, which would be catastrophic for life, but gravitationally nothing would change. Black holes don't suck things in any more than stars do. They don't have some special attractive force. They simply have gravity like everything else with mass, and objects follow the curved paths through space-time that this gravity creates. If you're far enough away from a black hole, its gravity is weak, just like being far from any massive object. It's only when you get very close, within a few times the radius of the event horizon, that the gravity becomes strong enough to be dangerous. The concept of space-time curvature is central to understanding black holes. In Einstein's general theory of relativity, gravity isn't a force pulling on objects. Instead, massive objects curve the fabric of space-time around them. Objects follow straight paths through this curved space-time, and these straight paths, called geodesics, appear to us as curved paths through space. Earth orbits the Sun not because the Sun is pulling on Earth, but because Earth is following a geodesic through the curved space-time around the Sun. Black holes take this to an extreme. The curvature of space-time around a black hole becomes so steep that at the event horizon, the geodesics point inward. All possible futures lead toward the singularity. That's why nothing can escape from inside the event horizon. There is simply no path through space-time that leads back out. It's not that the gravity is pulling too hard for anything to escape. It's that the structure of space-time itself has become such that outward doesn't exist as a direction inside the event horizon. This might sound disturbing, but from a certain perspective, it's beautifully simple. Black holes are just following the mathematics of general relativity to their logical conclusion. There's nothing mysterious or supernatural about them. They're natural consequences of how space-time behaves when enough mass is compressed into a small enough volume. One of the most fascinating features of black holes is time dilation. According to general relativity, time passes more slowly in strong gravitational fields. Near a black hole, this effect becomes extreme. If you could watch someone falling toward a black hole from a safe distance, you'd see them moving more and more slowly as they approached the event horizon, their image becoming increasingly redshifted and dim. They would appear to freeze at the event horizon, never quite crossing it from your perspective, because the time dilation becomes infinite there. Of course, from the perspective of the person falling in, nothing special happens at the event horizon. They cross it in a finite amount of their own time, though they're doomed once they do. This means that, in a sense, Nothing ever quite falls into a black hole from the perspective of outside observers. Everything piles up at the event horizon, frozen in time, growing dimmer and dimmer until it fades from view. Yet, from the perspective of the infalling material, the journey continues normally. It's a profound demonstration of how space-time and motion are relative, how different observers can have fundamentally different but equally valid experiences of the same events. Black holes aren't completely black. In 1974, Stephen Hawking predicted that black holes should emit a faint glow of thermal radiation due to quantum effects near the event horizon. This Hawking radiation is extraordinarily faint for any black hole large enough to have formed from a collapsed star. Far too faint to be detected with current technology. But it's there in principle, and for very small black holes it would be stronger. Hawking radiation means that black holes very slowly evaporate over time, losing mass and shrinking. For a stellar mass black hole, this evaporation would take far longer than the current age of the universe, more than 10 to the 67th power years. But eventually, given enough time, even the largest black holes will evaporate completely. Not all black holes form from collapsed stars. At the centers of most galaxies, including our own Milky Way, there are supermassive black holes containing millions or billions of times the Sun's mass. Our galaxy's central black hole, called Sagittarius A star, has a mass of about 4 million times the Sun's mass. Its event horizon has a radius of about 12 million kilometers, about 17 times the radius of the Sun. Despite this enormous mass, Sagittarius A star is currently quite quiet, not actively consuming large amounts of material. It just sits at the galactic center, its gravity helping to hold the galaxy together, stars orbiting around it just as planets orbit stars. Some supermassive black holes are actively feeding, pulling in gas from their surroundings. When this happens, the infalling material forms an accretion disk, a swirling disk of gas and dust that gradually spirals inward toward the event horizon. Friction in the accretion disk heats the material to millions of degrees, causing it to emit enormous amounts of radiation. So much that actively feeding black holes can outshine all the stars in their host galaxies combined. These are what we call active galactic nuclei or quasars when they're especially bright. Quasars are among the brightest objects in the universe, visible across billions of light-years of space, powered by black holes consuming matter at rates of multiple solar masses per year. Yet even these spectacular objects are following natural laws. The light from a quasar comes from the accretion disk, not from the black hole itself. The black hole remains dark, but the material around it, heated by friction and compression as it spirals inward, glows brilliantly. It's a demonstration of how gravitational potential energy converts to thermal energy and then to light. The process is violent on small scales, material colliding, atoms being torn apart, intense magnetic fields, but the overall structure, the formation of an accretion disk, the conversion of gravitational energy to radiation, is a natural consequence of how matter behaves around massive objects. One of the most remarkable discoveries in recent years was the first direct image of a black hole. In 2019, the Event Horizon Telescope collaboration released an image of the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The image shows exactly what general relativity predicts: a dark central region, the black hole's shadow, slightly larger than the event horizon due to light-bending effects, surrounded by a bright ring of glowing gas in the accretion disk. It was stunning confirmation that our theoretical understanding of black holes is correct, and it was a testament to human ingenuity that we could image something so distant and exotic. In 2022, a similar image was released of Sagittarius A star, our galaxy's central black hole. Though closer than M87's black hole, Sagittarius A star is much smaller and its accretion disk is more variable, making it actually more challenging to image. But the result was similar. A dark shadow surrounded by a bright ring, exactly as predicted. We have now directly imaged two black holes, and both match theoretical predictions beautifully. Black holes, despite their extreme nature, exist peacefully in the cosmos. They follow the same laws of physics as everything else. They don't violate any principles. They don't break any rules. They simply take the equations of general relativity and push them to their limits, showing us what happens when gravity becomes truly dominant. And what happens is elegant. Space-time curves so much that it closes in on itself, creating regions from which no information can escape, bounded by surfaces where time and space exchange roles in a sense, surrounded by zones where time passes at different rates depending on how deep in the gravitational well you are. There's a certain peace in understanding that black holes are solutions to Einstein's equations, just mathematical expressions of how space-time curves in response to mass. They're not malevolent. They're not conscious. They don't hunger or desire. They simply exist, warping space-time around themselves, creating the structure of space and time that any objects nearby must follow. Stars orbit supermassive black holes just as planets orbit stars, following geodesics through curved space-time, stable in their orbits for billions of years. As you rest tonight, know that at the center of our galaxy, a black hole with 4 million times the sun's mass sits peacefully, stars orbiting around it in a cosmic dance that's been ongoing for billions of years. That black hole isn't threatening those stars. They're perfectly safe in their orbits, following the paths that space-time geometry dictates. The black hole is simply part of the structure of the galaxy, a consequence of how matter has collected and evolved over cosmic time. In galaxies across the universe, billions of black holes exist, from stellar mass black holes scattered throughout galaxies to supermassive black holes in galactic centers. They're part of the cosmic ecosystem, products of stellar evolution and galactic formation, following the same laws as everything else. They remind us that the universe can be extreme, densities approaching infinity, gravitational fields strong enough to trap light, regions where time dilates enormously. Yet even these extremes are governed by comprehensible mathematics, by equations we've discovered and verified. Let the elegance of black holes soothe you. They're not chaos or destruction. They're order and geometry, space-time following its own rules, creating structures that would seem impossible if we didn't have the mathematics to describe them. Rest in the knowledge that even the most extreme objects in the universe behave lawfully, predictably, in accordance with principles we can understand. The universe makes sense, even at its most exotic edges, and that sense-making is one of the most peaceful realizations we can have. The cosmic calendar, deep time and perspective. One of the most profound ways to find peace is to contemplate the immense stretches of time over which the universe has been unfolding. Our everyday worries and concerns, the things that keep us awake at night, exist within the context of cosmic timescales so vast that they make even geological time seem brief. When we step back and view our lives against the backdrop of billions of years of cosmic history, perspective naturally emerges, and with it, a certain calm. Imagine condensing the entire history of the universe, all 13.8 billion years of it, into a single calendar year. This is sometimes called the cosmic calendar, a concept popularized by Carl Sagan. In this calendar, the Big Bang occurs at the stroke of midnight on January 1st, and the present moment occurs at midnight on December 31st. Let's walk through this calendar and see where everything fits. January 1st, midnight. The universe begins in an intensely hot, dense state. In the first second, the fundamental forces separate, elementary particles form, and the universe expands at an incredible rate during a period called inflation. By the end of the first day, representing about 40 million years, the first atoms have formed and the universe has cooled enough for light to travel freely, creating the cosmic microwave background radiation. January progresses with the universe expanding and cooling. The cosmic dark ages begin, a period when the universe was filled with neutral hydrogen but had no sources of light. Not until late January, representing about 200 million years after the Big Bang, do the first stars begin to form, ending the dark ages and beginning the epoch of reionization as ultraviolet light from these first stars reionizes the hydrogen gas filling space. February through most of March sees the formation of the first galaxies. These early galaxies are small and irregular by today's standards, but they're the seeds from which modern galaxies will grow through mergers and gradual accumulation of matter. During this time, the first generation of massive stars live their brief lives and explode as supernovae, enriching the interstellar medium with heavy elements for the first time. By mid-March, galaxies have begun to take on more recognizable forms. Spiral galaxies, elliptical galaxies, and irregular galaxies exist throughout the universe. The basic large-scale structure of the universe, the cosmic web of filaments and voids, has emerged, with galaxies concentrated along the filaments. April and May see continued galaxy formation and evolution. The rate of star formation in the universe reaches its peak and then begins to decline as more and more of the available gas gets locked up in stars or heated to temperatures too high for star formation. Supermassive black holes grow in galactic centers, some of them becoming active quasars, while others remain relatively quiet. June through August sees the universe continuing to mature. Galaxies collide and merge, creating larger galaxies. Stars form, live their lives, and die, recycling their material back into the interstellar medium. The universe continues to expand, with the expansion rate gradually decreasing but never reaching zero. Though around this time something changes. Dark energy, which has been present all along, begins to dominate the dynamics of the universe, and the expansion begins to accelerate rather than decelerate. Throughout all of this time, January through August, nothing that we would recognize as our solar system exists. Earth hasn't formed yet. Our sun hasn't formed yet. In fact, our sun couldn't have formed yet because the materials needed to form rocky planets like Earth, elements heavier than hydrogen and helium, had to be created first in multiple generations of stars. Not until early September, representing about 9 billion years after the Big Bang, does our solar system begin to form. A cloud of gas and dust, enriched with heavy elements from previous generations of stars, begins to collapse under its own gravity. By mid-September, the Sun has ignited fusion in its core and the planets are forming from the debris disk around it. Earth forms along with the other rocky planets. Late September sees the formation of the Moon, probably through a giant impact between the young Earth and a Mars-sized body. The early solar system is a chaotic place, with frequent collisions as the planets clear their orbits of remaining debris. Impacts are common, and some of these impacts may have delivered water and organic compounds to Earth. October is when life appears on Earth. By early October, representing about 3.7 billion years ago, the first simple single-celled organisms have emerged. These are prokaryotes, cells without nuclei similar to modern bacteria. They're simple by our standards, but they represent an extraordinary development. Self-replicating chemical systems, the first life on Earth. Throughout October, November, and much of December, life on Earth consists entirely of single-celled organisms. These organisms gradually evolve and diversify. Some learn to perform photosynthesis, producing oxygen as a waste product. Over hundreds of millions of years, weeks and months on the cosmic calendar. This oxygen accumulates in Earth's atmosphere, eventually reaching levels similar to today's. This atmospheric oxygen is toxic to many of the organisms that evolved when Earth's atmosphere was oxygen-free, but it opens up new possibilities for those organisms that can tolerate or use it. Not until mid-December, representing about 600 million years ago, do complex multicellular organisms appear in the fossil record. This is the Cambrian explosion, a period when animal life rapidly diversified. Within a few tens of millions of years, just days on the cosmic calendar, representatives of most major animal groups appear in the oceans. December 15th, the first land plants appear, beginning the greening of Earth's continents. December 19th, the first land animals venture out of the water. December 20th through 22nd, the age of dinosaurs begins and continues, spanning the Triassic, Jurassic, and Cretaceous periods. Dinosaurs dominate the land for over 170 million years, yet on the cosmic calendar, their entire reign lasts only about 3 days. December 26th, an asteroid impact ends the age of dinosaurs. The impact creates a crater about 180 kilometers in diameter in what is now the Yucatan Peninsula, sends ejecta around the world, triggers fires, and blocks out the sun for months or years. The dinosaurs, along with about 75% of all species on Earth, go extinct. But this catastrophe opens ecological niches for mammals, which had existed alongside dinosaurs for over 100 million years, but had remained small and relatively inconspicuous. December 27th through 31st morning, mammals diversify and spread across the continents. Primates appear. The continents continue to drift, reaching configurations closer to what we see today. Ice ages come and go. The climate fluctuates. December 31st, 6 in the morning. Our hominin ancestors diverge from other great apes. This is about 7 million years ago, just 18 hours on the cosmic calendar. December 31st, late evening, around 10:30 p.m., modern humans, Homo sapiens, appear in Africa. All of recorded human history, the entirety of human civilization, from the first cities to the present day, occurs in the last 21 seconds of the cosmic year. The pyramids of Egypt are built about 10 seconds before midnight. The Roman Empire rises and falls in the last 6 seconds. The Renaissance, the Scientific Revolution, the Industrial Revolution, the entire modern era, all of it occurs in the last second of the cosmic year. Your entire life, every moment you've experienced, every memory you hold, every worry that keeps you awake at night, all of it exists in a tiny fraction of the last second of December 31st. In cosmic time, a human lifespan is barely a blink. The entire span of human civilization is almost imperceptibly brief. This isn't meant to make you feel insignificant, though it does put things in perspective. Rather, it's meant to be liberating. The anxieties that weigh on us, the regrets, the fears about the future, these are all confined to an incredibly small window of cosmic time. Meanwhile, the universe has been unfolding for 13.8 billion years. Stars have been forming and dying, galaxies have been colliding and merging, the cosmic web has been taking shape. All of this vast cosmic drama has been playing out, following natural laws, creating increasing complexity and beauty, and we're fortunate enough to be here, at this particular moment, able to observe and understand it. Consider the atoms in your body. Every atom heavier than hydrogen was forged in the core of a star, possibly billions of years before Earth even existed. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was created by fusion reactions in stellar cores or in the brief moments of supernova explosions. These atoms scattered into space when those ancient stars died. They drifted through the interstellar medium for millions or billions of years. Eventually, they became part of the cloud of gas and dust that collapsed to form our solar system. They condensed into planets. They became part of Earth. They cycled through rocks, through oceans, through atmosphere, through countless living organisms, and eventually they became part of you. You are made from ancient stardust. The atoms in your hand might come from dozens of different stars, each with its own history, each having lived its life billions of years ago in some distant part of the galaxy. These atoms are older than the sun, older than Earth, older than anything in the solar system except the most primitive meteorites. They're cosmic relics, and they're part of you. This continuity through time is profound. You're not separate from the universe, you're a temporary arrangement of universal matter, a brief configuration in the endless recycling of atoms that has been going on since the first stars formed. When you die, your atoms will be recycled again. They'll become part of the Earth and eventually part of other living things, other structures, other temporary arrangements. Nothing is truly created or destroyed. It's all just matter and energy changing forms, following the laws of physics, participating in the great cosmic cycle. There's deep peace in recognizing this. Your existence is temporary, yes, but it's also part of something eternal. The matter that makes you up has existed for billions of years and will continue to exist for billions more. You're a wave in the ocean, a temporary pattern in something much larger and more enduring. The wave rises, exists for a time, then subsides back into the ocean. But the ocean remains. Thinking on these timescales naturally creates perspective. Whatever you're worried about right now exists in the context of cosmic time. The universe has been here for 13.8 billion years. It will likely continue for trillions of years more. Earth has existed for 4.5 billion years and will likely remain habitable for another billion years or so before the slowly brightening sun makes conditions too harsh for life. Humanity has existed for perhaps 300,000 years and might exist for hundreds of thousands or millions of years more, or we might not. Civilizations rise and fall. Species go extinct. Continents drift. Ice ages come and go. And through it all, the universe continues its patient expansion. Stars continue to shine. Galaxies continue to orbit and merge. The fundamental processes continue. This doesn't mean your concerns don't matter. Within the context of your life, of human life, they matter very much. But it does mean that you can let go of the weight of thinking everything depends on you, that any mistake is permanent, that any failure is final. In cosmic time, nothing is permanent except change itself. Everything is temporary. Difficulties pass, joys pass, we ourselves pass. And this temporary nature, rather than being depressing, can be freeing. We can experience and appreciate what we have while we have it, knowing that it won't last forever, that it's part of a much larger pattern. The universe doesn't judge. It doesn't care about your successes or failures, your accomplishments or mistakes. It simply continues, following its laws, unfolding according to physics and chance. There's no cosmic scorekeeper, no ultimate authority evaluating your life. There's just the universe, beautiful and vast and indifferent, and you, a small conscious part of it, temporarily aware, temporarily able to observe and understand. Make of that what you will. As you lie here tonight, in the last tiny fraction of the last second of the cosmic year, consider how fortunate you are. You exist at a time when the universe has had enough time to create stars, to create heavy elements, to create planets and life. You exist in a location and time where conditions are right for complex life to exist. You exist with consciousness, with the ability to think about and understand the universe you're part of. This is an extraordinary privilege, one that most of the matter in the universe will never experience. The universe is 13.8 billion years old. You might live for 80 or 90 years if you're fortunate. That's about 6 billionths of the age of the universe. You're here for this brief moment, able to experience, to think, to feel, to observe the stars and understand what they are. The universe has taken on a form, your form, that allows it to be conscious of itself, if only for this brief span of time. Let yourself feel held by deep time. Your individual life is brief, yes, but it's part of a story that's been unfolding for billions of years and will continue to unfold for billions more. You're a chapter in an enormous book, a brief note in an endless symphony, a small wave in a vast ocean. And that's not diminishment, that's connection. You're part of something much larger than yourself, something ancient and ongoing, something that includes all the stars and galaxies, all of space and time, all of existence. Rest in that perspective. Let the weight of cosmic time be a comfort rather than a burden. Your worries and concerns are real within the context of your life, but in the larger context of cosmic history, they're as brief as they are insignificant. This doesn't mean you shouldn't care about things. It means you can release the crushing weight of thinking everything matters cosmically. Most things don't matter on cosmic scales, but they can still matter to you, to the people you care about, within the brief span of time you have. The universe will continue long after you're gone. Stars will keep shining, planets will keep orbiting, galaxies will keep evolving. The cosmic calendar will continue into its next year, and the year after that, and the year after that. And all of this will happen according to the same laws that have governed it since the beginning. There's a profound peace in this continuity, this persistence, this lawfulness. We are temporary, but the universe is very nearly eternal, and we're part of it for this brief, precious moment. Let cosmic time hold you as you fall asleep. You are ancient stardust temporarily arranged in a form that can think and feel and wonder. You're part of a story 13.8 billion years in the making. You're connected to everything through time and through matter, through the atoms in your body that came from dying stars, through the laws of physics that govern your existence just as they govern everything else. Rest in that connection. Let it be a comfort as you drift toward sleep. We've journeyed together through the cosmos tonight, floating through the most peaceful and awe-inspiring aspects of our universe. We've contemplated the vast scale of the observable universe, stretching 46.5 billion light-years in every direction, uniform and democratic in its structure. We've explored the patient lives of stars, burning steadily for millions or billions of years in perfect equilibrium. We've observed planets in their predictable orbits, following the same paths they've traced for billions of years and will continue to trace for billions more. We've experienced the gentle rain of light and electromagnetic radiation that connects us to distant corners of the cosmos, from the ancient photons of the cosmic microwave background to the steady glow of nearby stars. We've considered comets, asteroids, and meteors, timeless travelers that have been following their orbits since the solar system formed, occasionally providing us with spectacular displays as they pass through our skies or burn up in our atmosphere. We've marveled at the beauty of nebulae, the cosmic gardens where stars are born and where dying stars return their enriched material to space. We've contemplated the elegant geometry of black holes, regions where space-time curves so intensely that not even light can escape, yet which follow mathematical laws just like everything else in the universe. And we've gained perspective from considering deep time, the vast stretches of cosmic history that dwarf our brief human existence yet connect us to everything through the ancient atoms in our bodies. All of these phenomena share common themes. They're governed by natural laws, gravity, electromagnetism, quantum mechanics, relativity. They unfold on timescales that are vast by human standards, yet every process follows a predictable pattern. They demonstrate that the universe, despite its immensity and complexity, operates according to principles we can understand. And they invite us to step back from our immediate concerns and see our lives in the larger context of cosmic existence. The universe doesn't rush. It doesn't hurry its processes or skip steps. Stars take millions of years to form, billions of years to burn through their fuel. Galaxies take billions of years to grow and evolve. Light takes years, centuries, or millennia to travel from distant stars to our eyes. Even the universe's expansion, constantly ongoing, is so gradual that we can only detect it by carefully measuring the light from distant galaxies. Everything proceeds at its own pace, following the laws of physics, creating beauty and complexity through simple processes repeated countless times. There's a profound lesson in this patience. We live in a world that often feels rushed, where everything seems urgent, where we're constantly pressured to hurry, to do more, to be more. But the universe reminds us that the most important processes, the ones that create stars and planets and life itself, take time. They can't be rushed. They unfold at their own pace, and they do so beautifully. You can carry this perspective with you. When you feel rushed or pressured, remember that you're made of atoms that took billions of years to create, that drifted through space for millions of years before becoming part of Earth, that cycled through countless configurations before becoming part of you. There's no cosmic stopwatch measuring your productivity. There's only the patient unfolding of the universe, of which you're a small but authentic part. When you feel small or insignificant, remember that you're part of a universe 13.8 billion years in the making, that you're conscious stardust, temporary but real, brief but meaningful within your own context. You're connected to everything through matter and through physical law. The same forces that hold galaxies together hold your body together. The same processes that created the sun created you. You are not separate from the cosmos. You are the cosmos, temporarily arranged in a form that can think and feel and wonder. When you feel anxious about the future, remember that the universe has been here for billions of years and will be here for billions more. Stars will continue to shine. Planets will continue to orbit. The cosmic microwave background will continue its gentle glow. The fundamental processes will continue. Whatever happens in your life, however things turn out, the universe will continue its patient unfolding. This isn't meant to diminish your concerns, but to remind you that you're held by something much larger and much more enduring than any individual worry or fear. As you drift fully into sleep now, let all of this settle into your consciousness. Let the vastness of space be a comfort rather than a source of anxiety. Let the patience of cosmic time soothe your urgency. Let the lawfulness of the universe remind you that there's order underlying the apparent chaos, that everything follows patterns, that we can understand and predict and find meaning even in the most enormous scales of existence. The stars are shining above you right now, just as they've been shining for billions of years. The Earth is following its orbit around the sun, just as it has for 4.5 billion years. The galaxy is slowly rotating, taking about 200 million years to complete one turn. The universe is expanding, carrying distant galaxies away from us, continuing the process that began with the Big Bang 13.8 billion years ago. All of this is happening whether you're awake or asleep, whether you're worried or calm, whether you're paying attention or not. The cosmos continues its ancient dance, and you're part of it. Before I let you go completely into restful sleep, I want to ask a favor. If you've enjoyed this journey through the peaceful facts of astronomy, if you found some comfort or perspective or simply some interesting things to think about as you drift off, please consider leaving a like on this video and subscribing to the channel. Your support helps me create more content like this. Long-form, relaxing explorations of science and nature designed to help you sleep while also satisfying your curiosity about the universe. If there are particular topics you'd like me to cover in future videos, whether astronomical, geological, biological, or any other area of science, please leave a comment and let me know. I read all the comments, and your suggestions directly influence what content I create next. This channel exists for you to help you find peaceful rest while also feeding your mind with interesting, accurate scientific information. Thank you for spending this time with me tonight, floating through the cosmos, exploring the most peaceful aspects of our universe. May your sleep be as deep as space, as peaceful as a star in equilibrium, as patient as the cosmic cycles we've explored together. Rest well, knowing that you're part of something ancient and beautiful and vast, something that will continue long after you've woken, something that connects you to everything in existence. Good night, fellow Stardust. Sleep peacefully under the stars.